Greetings. Welcome to day 2 of the Rambus Design Summit 2023. My name is Neeraj Paliwal. I lead the Silicon IP business for Rambus. During this session, we'll talk about emerging security challenges in highly interconnected semiconductor systems. We'll unpack this complex topic in 3 parts. Number 1, why does security matter more now? What are the emerging challenges? Number 2, in terms of securing the data and devices when it comes to AI, edge, and communication segments. Number 3, how do we solve these challenges, both with the existing solutions we have, like traditional cryptography, and the research required to come up with new solutions, like post-quantum, quantum-safe engine, as well as homomorphic encryption and dealing with adversarial AI problems. Let's get started. Let's get to the topic number 1. Why does security matter even more now than ever before? Well, you see in the interconnected systems where you have lots of chiplets on an interconnected system, that is a challenge in terms of how you can trust those various chiplets on the system, as well as on the supply chain side. So in a way, increased complexity of the supply chain driven by these new suppliers and technologies really make it harder for securing that system. The second thing we are seeing is there is an exponential increase in the data that is being acquired by each sensor. New information from IEEE, RDS published documents from last year say over 75% of enterprise-generated data will actually live on the edge devices, not on the data center. So there is a clear trend to bring that data away from the data centers, locked and secure data centers. We also see there is a clear paradigm shift here, where earlier we were moving data to the compute. Now the compute is moving to the data. What we mean by that is that those edge devices are going to have AI processing done on the edge, primarily from you have issues related to energy efficiency, bandwidth, latency, and not to mention the security. Well, how did we get here? Why do we have so many different new design starts that work on accelerated compute? We call them heterogeneous compute. The main reason is really over the last 2 decades, Moore's law has been slowing. And as Moore's law has been slowing, along with it, we see almost an end of Dennard scaling, as well as all these things combined together. You could say that technology is not able to keep pace with the demands that are coming from today's new AI workloads. So on one hand, you see an explosion in number of parameters and how big these AI algorithms and models are becoming, and the technology is not able to keep pace with it. That's why we need to now have purpose-optimized chips to do, whether it's video encoding or just looking at the generative AI and the kind of chips that are required for that. As these new chips are being developed by emerging new system design companies like the Googles, instead of being designed by all of them, mostly by the x86 and some of the other companies, traditional semiconductor companies, you will see more and more focus on optimizing the performance of AI, working on the software for these system design companies. And many of these chips will be vulnerable without a reliable security IP vendor. And that's why more and more of these chips are now relying on industry standard differentiating IP. We earlier touched upon data center, how the data is being generated more and more away from the data center. And here you could see the amount of data that's going to be generated by each year by 2032, 10 to the power 27. And that data, when it's being generated away from the data center on the edge, it would be impossible to move that data over to the data center to process for any kind of AI applications. The backbones and the communication networks just won't be able to support it. So a new paradigm shift is required to process that data, to admit that data at the edge into an economic activity. And that would require new protocols and trust and control mechanisms right on the edge devices in order for us to do it securely. Related trend is on the AI processing side. That's now happening on the IoT edge devices, as well as all the sensors, cyber physical systems. And that's really creating a demand on continuously evolving the data analytics, AI models, inference value. And what that means in terms of security challenges, we need to figure out on these devices, how do we do secure over-the-air updates like your cars and your phones have been doing for almost 5 to 10 years now seamlessly. How do we get the security on edge devices, billions and trillions of these edge devices over the next 10 years at the same level as the phone on your palm? In addition to securely updating your phone's firmware, data attestation, secure integration, and deployment is another challenge that you will see. So overall, what you see as a result of AI-driven edge processing, the whole security threat landscape changes significantly from where it was 5, 7 years ago, where most of the data was being processed on the data center, to now becoming on the edge devices that are not necessarily in physical control, like your phone or your laptop. And that creates the challenge on security side. Some of the examples of these challenges, if you open any newspaper or browse through any of the magazines that cover technology, or even general newspapers, you will see new information coming out, whether it's ransomware attacks or whether it's attack on our hospital system or cybersecurity vulnerability, DDoS, all those things. And as a result of these challenges and these vulnerabilities, governments are starting to take notice. And that's resulting in regulations. For example, just on the data side, it started with Europe coming up with GDPR, privacy-related regulation. In US, we have had HIPAA for a long time, but in the truly virtual call with your doctor and keeping all your health records online, it takes a new meaning. What you see on the cybersecurity, on the automotive side, 20 years ago, the cars were not a connected computer. If you look at it now, automotive is in a way leading all other segments except defense with regulations when it comes to cybersecurity. You would see the automotive standards even come into the edge devices. In a way, we could say car is also an edge device, but if we were to differentiate the two, US government as well as EU have their own cybersecurity act, and a lot of the other things are happening in terms of purchasing as well. Government in today's geopolitical environment is getting very sensitive around securing their own infrastructure and the devices and data for their citizens. So how do we solve these? Now we come to the third part. Traditionally, it was always good practice to embed security at the hardware level. So that way you have a true anchor in hardware that is connected to non-volatile memory, so you can secure your secrets. Primarily, we do certain application use cases with the traditional security. We secure the keys, either by a secure element or a root of trust. We secure the firmware and any over-the-air update in case the device is hacked or just a regular update. And that is done with secure boot applications as well as update managers and signed updates that we send. In addition to that, we provide security in terms of biometrics and password managers when we secure with the smart card, or nowadays embedded secure card equivalent function as part of the HSM on your own SoC. And that became commonplace starting from iPhone 5S when Secure Enclave was connected, built inside an A-class Apple chip. Last but not the least, there are secure development processes that keep us away from limiting attack surface, fighting feature creep, vulnerability that it comes. A lot of these applications are already existing, how you do things. However, there is a lot more that's changing as you move forward. We all hear a lot about quantum safe encryption, quantum safe engines. How are we going to secure our devices and our data in a post-quantum world? We hear a lot about post-quantum, and there is a lot of confusion. So I'll try to unpack two things at a layman term. One, why is post-quantum cryptography or quantum safe engine important? You will hear, and it's a right argument, we don't have any general availability of quantum computers right now. For example, you can't go on AWS or Azure and buy a CPU or a processing element that has quantum compute on it. So why are we talking about quantum cryptography? That's one thing. Well, the reason is really simple. If you want to use quantum computers to do generative AI, that is 5 to 10 years away, minimum. But a state actor can easily have powerful enough quantum computer that is not in commonplace on the data centers right now that they can use to attack one particular infrastructure at a time. For example, enemy combat, whether it's a Cold War or actual war-like situation, or you just want to gather information on your enemy or a competing country, there are ways on how you can break public key cryptography as of today using some of those installations. I mean, it may not be public knowledge, but if you talk to state agencies or what we are speculating, that kind of capability can exist today. So while quantum computers are not commonplace for everybody to do their chat GPT with it, but for state actors or for resourceful entities, it is possible to launch attacks because all it takes is one capable quantum compute installation to be able to attack public key cryptography or ECC or RSA. Now that we have cleared why people are talking about it, why NSA and all major governments are making it more and more a regulation as part of safeguarding their own infrastructure, both government and citizen infrastructure, let's get into the second part. Well, how is public key cryptography breaking when it comes to quantum computers, and why it doesn't break or it works when it comes to traditional computers? Turns out the asymmetric cryptography, some part of it, to break RSA, we rely on some two large prime numbers and multiplying them, and then it's hard to decode that, to learn those secret primes if you use 0-1 based digital computers, traditional compute elements. When we go into math of it a little bit, I'll skip over the math, but as you can see here on the slides with QPE and quantum Fourier transform, what may take 100 or 1,000 years for a traditional computer can actually be solved with a quantum computer in a matter of 15 minutes to half an hour. And that really creates the vulnerability. And all you need is one capable quantum compute cluster to be able to mount and launch these attacks. What do we need to do? So that's a lot of challenges, and we have unpacked a little bit why quantum computing is important and how does it break RSA. In order for us to upgrade our installation of traditional security with quantum safe crypto, we will have to undertake a massive effort to upgrade IoT devices and services that are high risk or that are likely to be impacted. Governments around the world need to push this and accelerate the transition. There is standardization in progress, but there's no major standards yet, except for secure boot in LMS, XMS. And so one could say this is a rapidly evolving situation. And it's going to be work in progress for the next 15 years. Rambus cryptography, at the leading edge of this technology, last week, early July in 2023, we have launched general availability of our marquee product, CMRT, Crypto Manager Root of Trust 2.0, and that includes quantum-safe cryptography implementation. We're really proud of the work the teams have done. However, it is a work that will require a lot more efforts over the coming years as new schemes and new algorithms are announced by NSA. So after this, let's take a look at a little bit more countermeasures and other invasive attacks that require the countermeasures. There are a lot of physical attacks that are happening on the edge that may not be possible in a data center environment because that was locked and physically in security and protection. Side channel attacks, Rambus has been leading the DPA technology for the last 25 years. We have DPA implementation on every one of the cores that we do, whether it's symmetric or asymmetric crypto. And the solutions that we provide for inline crypto as well includes the side channel attack protection. There is also industry-leading work we are doing. So our AES and PKE engines are both DPA and FIA resistant. This is a type of work that is not table stake for a new company to come and start implementing. We have robust knowledge with the foundational elements over 2 decades in these areas. And the market is just catching up to this if you look at the industry and the other players. We believe this will continue to become a table stake as we move forward, FIPS 140-3, and as these attacks become more relevant. Switching gears from the edge now into AI. I mean, this is really fun part. So there is a company called Capable, and there is an underscore CAP_ABLE. It's a fashion brand. I mean, it's not a tech company. They use tech. The concept is really simple. Many of us are sick and tired of these facial recognition cameras that actually follow us everywhere. So privacy becomes an issue. So what this company does, they sell you clothing that has random pattern. And that pattern fools AI on the facial recognition camera systems to make the system that's processing your image as you walk through the mall or through the country square. It basically fools it and says, instead of this being Neeraj, it's actually an animal like a giraffe or a dog or a bird. So whatever the picture is there, they're trying to fool it. And this is the most layman way of explaining what adversarial AI attacks mean. Natural intelligences can be tricked. And there are no, as far as we know, this is a hot research topic. There are no countermeasures available in the marketplace that we are aware of. And this is an area where we are looking into, and this could become really, really important as AI becomes prevalent everywhere in our day-to-day lives. Similarly, when it comes to securing computations, when what we say, while the data is still in use, or you don't want to decrypt, encrypt and decrypt the data, and fully homomorphic encryption actually allows us to do processing the data without actually decrypting it. And so really cool technology, uses some of the basic ideas to compute only on the encrypted data. However, it is not practical today from a latency point of view as well as energy point of view to implement it in a hardware accelerator. This is another emerging technology which, when we talk about traditional or the post-quantum, those things are in place now. But some of these technologies like homomorphic encryption and adversarial AI, we still are doing groundbreaking research and trying to come up with solutions for these challenges. Similarly, if you go to securing the cars, securing the sensors around the cars, those are also some of the challenges we are working with. And our research team continues to look into these challenges. As a summary of this, we started from why security matter more today in a highly interconnected system, which our semiconductors are becoming now, whether it is a data center or edge or a car. We looked into the solutions that exist, and then we looked into a couple of areas that are still challenges we need to solve. It's really a fun area to be working, and we're really proud to be at the leading edge of this. We always say we are on a mission to secure the semiconductors and its supply chain. And we look forward to hearing from you, see if there is any way we can help you build secure, interconnected semiconductor systems for the future. Thank you.